chapter 19, and this is about using the principle of angular momentum and impulse in for rigid bodies. So the previous chapter was particles, this is for rigid bodies. So the formula is essentially extension of what we did for particles. So let's define a few things. Linear and angular momentum. Okay, so we're looking at a rigid body which clearly has a center of mass. Let's call this point G, where the center of mass is located. This particular body has an angular velocity omega and a linear speed or translational speed of Vg. And I wrote omega as a scalar because we are doing only planar motion, so omega is pointing in the k direction. So the linear momentum is the same as what we define for a particle. It is just mass times the velocity. L is mass times velocity of the center of mass. The angular momentum is denoted by hg, and that's actually a vector, but I'm going to write it as a scalar because angular speed is a scalar. It is in the k direction. So hg is ig times omega. So this was missing for a particle, right? Because Ig for a particle is 0, so Hg is 0. Or a particle, in other words, well, it doesn't have really angular speed because it's a particle, so omega is 0. So you could interpret this Ig is 0 or omega is 0 for a particle. That's why Hg is 0. Now, when we talk about a rigid body, there can be three cases. There could be, the rigid body could be translating, it could be rotating about fixed axis, or it could be a general planar motion. So if you see a problem where it's translating, then the linear momentum remains the same as what we defined it, but the angular momentum is simply 0 because a body which translates doesn't have angular speed. The second is rotation about fixed axis. Let's call that fixed axis O. So when you have this case, the linear momentum does not change, but for the angular momentum, you have two choices. You could write hg about h about g, or sometimes it's better to write HO equals I times IO times omega, where IO is IG plus mass times length GO square, where O is the distance between, O is the point at which the rigid body is rotating, and GO is LGO is the distance between O and G. And then finally, general planar motion. So this happens when the rigid body can translate as well as rotate. Right? Example would be a disk which is sliding or disk which is rolling. Yeah, question?
Number 2, would L be 0?
L will not be 0 because Vg is still not equal to 0. So an example would be a pendulum. Right? This pendulum Vg is not equal to 0. So general planar motion, L again is mass times Vg, and Hg is Ig omega. You cannot write, well, if you want to write a formula like the other one, HO is I0 omega, then you're better off writing it using the instantaneous center. So H about the instantaneous center is I about instantaneous center times omega, where IC is the instantaneous. So when you write H equals I omega, like in the first one, you're really doing is you're trying to find the point which has zero speed. So O, in this case, this is O, has zero speed. So if you want to do it for a body which is which has general planar motion, then you want to find IC first, and then use HIC is IIC times omega. So for example, for a disk which is rolling, not slipping, the point of contact is the IC. And so you could find inertia about that point. This is IC. Pure rolling. Okay, provided it's not sliding, because if it's sliding, then this point is not going to have the IC is not going to be at the point I've shown, because that point is going to slip and its velocity is not equal to 0. So is that clear? Okay, last formula and then we should get started with problems. Okay. Okay, so we can write, just like particle, we can write principle of impulse and momentum. Okay, and since so for a particle we wrote down mvg1 plus the integral f dt. So f is the external force. You will sum all the external forces, integrate from t1 to t2 equals m times velocity of g2. So this is rigid body is moving and velocity vg. Effective force is to cause the velocity to change. If you want to find the velocity after the application of force after time t2, then this formula will help you. Now this is true for a particle, it's true for rigid body, but for a rigid body the additional thing you want to worry about is the angular momentum. So you could write a similar expression for the angular momentum, which says that hg, the initial angular momentum, plus the contribution due to the moment about g, is equal to the new angular momentum. Okay, note that I use g here, so I use g here. They have to be the same points about which you take the moments. You can't use g one place and o at the other place, or fixed at any other point. Okay, now for fixed axis rotation, it would be more convenient. So for example, a pendulum, it would be more convenient to write this formula as this T2 HO, where O is the point about which the rigid body is rotating, equals summation MO dt equals HO2. So you can write that formula about fixed axis. In fact, if you have an IC for general planar motion, you'll replace O with IC and you can proceed. So that would also be a valid way. The reason why you want to write it about O is because when you have rotation about fixed axis like this. If you take moments about this point O, then that point has, well, reaction forces, right? When you draw the free body diagram, when you write the moment equation about O, that equation, the reaction forces will have a contribution of 0 in this part. Reaction forces have 0 moment, right? Because the point of application is O and not something else. This is G. So if you had used this formula to find, uh, to use this form, use the first formula, then this mg, moment about G, would have the reaction forces coming in, and that is something which you avoid when you use the second formula, H about O. So the general rule is you want to choose the point O such that, remember previously we chose O such that the majority of the forces either pass through O or majority of the forces are normal to O, so that the moment arm is 0. This step really saves you a lot of time by choosing points judiciously. Okay, so this is the linear impulse and momentum equation. This is the angular impulse and momentum equation. This is the equation you want to use about fixed axis or if there's IC. Okay, questions? So the procedure is essentially same as previous. If you have a problem, draw the free body diagram. Once you draw the free body diagram, the question is what principle to use. If the question is to find velocity as a function of time, then these are the principles you want to use, because what you see in this equation is just the time which is coming up, t2, t1 to t2. If it's velocity as a function of distance, then you want to go to the previous chapter, conservation of energy and what is principle of work done, and then F equals ma works for all problems. Just that these are simpler tricks to get you done faster. Okay, so let's apply this on a problem. Okay, the double pulley consists of two wheels which are attached to one another and turn at the same rate. The pulley has a mass of 15 kilograms, so this is 15 kilogram, and radius of gyration of 0.11 meters. If the block A has a mass of 40 kilogram, determine the speed of the block after 3 seconds after a constant force of 2 kilonewtons is applied to the rope wrapped around the inner hub of the pulley. The block is originally at rest. So the force causes the mass A to move up, starting from rest. You're going to find the velocity at 3 seconds. So again, you can see that you asked to find velocity as a function of time. And when you see something like this, I would recommend using principle of angular impulse or linear impulse and momentum as opposed to using F equals ma. You could use F equals ma too. So if you're going to use it F equals ma, then you'll have to first find the acceleration of the system, which by the way is going to be a constant, I think. Yeah, it's going to be constant, and then you can use kinematic formulas to do it. So it's a perfectly valid way. Let's just draw the free body diagram and go from there. FPD. Okay, so there are two bodies whose masses are given to us. There's A and then there is the pulley. So I'm going to draw a free body diagram for both. Okay. So the first method is use F equals ma and moment equals g dot, solve for a, where this is a, the acceleration, then use kinematics to solve for v at t equals 3 seconds. Okay, so this could have been a question in the previous chapter when we talked about F equals ma. You could do it without using these things. But since its velocity is a function of time, we're going to try to use principle of angular impulse and momentum. Okay, so what we have is basically two formulas. There is linear impulse, right? And then there's angular principle of linear impulse and momentum, which says that mvg1, how it is related to mvg2. Okay, and then the other one is hg1, how that is related to hg2. So you want to do minimum work as possible. You do not want to, so you can see that there's a particle here, A. For a particle, you can apply only principle of linear impulse and momentum, right? Because it's a particle. The pulley is a rigid body because you're given the inertia. So you could apply both principles, linear impulse, and principle of angular impulse and momentum, which means that you have to write one equation for the small mass, so the mass, the particle, and two equations for the pulley. So that's, you could lay down the equations and see what the unknowns are. I'm pretty sure you have n unknowns, n equations, so three equations, three unknowns, solve it. However, if you want to take a shortcut, then you want to think, how can you get an expression for the velocity and not have to solve for the reaction forces? So the reaction forces are, there's VO, HO, about the pin joint, and there's the tension, right? If you take moment about point O, which is this point, then you'll eliminate effect of HO and VO because they pass through O. So the moment due to those forces are zero. However, tension is going to be in that equation, right? Tension will show up in that equation. And we don't want to solve for the tension because you're not asked to find the tension or anything like that. So in this case, it's actually better off to not use that free body diagram. It's you're better off using the free body diagram of the system consisting of the pulley plus the particle. And the only reason I would do that is because then tension will not show up in the equation. So this is what I mean. I would redraw the free body diagram like this. F mg ho vo, and then I'll keep the string. I'll not cut the string. I'll keep it like this. So now you can see that there's no tension showing up in this free body diagram because I've not cut the string. This is a joint free body diagram. It's the free body diagram of both the bodies. Okay. Now if I take the angular moment or use the principle of angular impulse and momentum about point O, then all the forces are known, or the moments due to all the forces are known. The only forces which I do not know about is HO and VO, but those act at point O, so they will not figure out in the equation. So here's what I mean. This is, by the way, rotation about fixed axis O, right? So HO1 plus MO T1, T2, Tt equals HO2. So the initial angular momentum is what? It's zero because everything is stationary. MO is, let's try to find moment about point O. So capital MG, H0 and B0 all act about point O. So the contribution to those three forces is going to be 0 because moment arm is 0. The only things which will contribute to the moment about O is capital F and mg. So mg has a moment arm of 200 mm, so 0.2 meters, and this is counterclockwise, right? If you hold the pulley about O and then apply force mg downwards, then the pulley will turn in the counterclockwise direction. F has a moment arm of, let's see, it's 75 mm, so 0.075. Okay, and that is going to be clockwise. If you apply force, hold the pulley at O and apply force F, it's going to turn the pulley in the clockwise direction, so negative F. Okay, HO2. So the final angular momentum is going to be that due to the pulley, right? Is that it? So this is the total momentum of the system, right? When I read HO, it's the total momentum of the system from the free body diagram. So pulley is clearly spinning, but mg is also spinning with it. So if I had drawn only a free body diagram of the pulley, then IO times omega would be the right formula. But since I'm including mg in the free body diagram, mg, the mass m, small m, is also going to contribute towards the moment. So this is going to be the radius, which is 0.2 times mass times velocity, r cross mv. Okay, so if I assume that the angular speed is counterclockwise, convention is positive counterclockwise, this is positive, and this is also going to be positive. Right, because it's turning counterclockwise and v is going down, so it's also going to be counterclockwise. Or v cross r cross mv is going to be counterclockwise. R is pointing that way, v is downwards, r cross v is a vector which goes, r is that way, so r cross v is going to be the vector pointing towards the direction of my thumb, which is in the k direction.
You did the last part is for the small one?
Yes.
Okay.
Okay, so in this, can I find relation v and omega? So no slipping. It's not given, but you can make the assumption that the string is not slipping. If it's not slipping, then v equals omega r. So HO2 is going to be, IO is going to be mk square. It's given, k is the radius of gyration is given to you. I'm going to write omega as, let me keep omega as it is, plus 0.2 m omega r. So this is, I subbed omega r as v as omega r. Okay, so we are all set now. Let's plug it in the equation. So initial momentum is 0. We got to take the integral from t1 to t2. Now the good part is that mg is a constant, capital F is a constant. It's just 2 kilonewtons or 20 kilonewtons. See, it's 2 kilonewtons, and it's a constant force. So if this is a constant, and so is this, the integral MO dt is going to be mg times 0.2 minus f times 0.075 times the total time. Just multiply the time, dt, right? It's going to be 3 minus 0 because it's over 3 seconds, equals mass times k0 square omega plus 0.2 m omega r. You sub in, this is comes out to be minus 214.56 equals minus 1.7815 omega. Sorry, it should be positive. So omega is 120.437. So we are asked to find V, which is omega times R. That is 24.027 meters per second. I just wrote the magnitude here. I ignored the sign in here. It should be negative. It should be negative. That's just saying that the velocity is downwards. Okay, hold on, I don't think that's right. So if the moment is negative, it means that F is greater than mg. So if F is greater than mg, I think it's going to move clockwise. So yeah, so omega is going to be clockwise. That's why omega is negative. So the pulley is pulled up. It doesn't go down. That's why that's the negative sign. Clockwise. So V is minus omega r. So V has to go upwards. I'm not sure if the sign doesn't look right to me. Any thoughts?
Should it be positive?
Well, it depends. The convention is V upward is positive. So this is saying that V is downwards. That's not true. V is upwards because eventually this thing is spinning clockwise, the pulley. Omega is right. I don't know about V. We got to. So let me think about this. Okay, so this is the 30 kilogram gear. Has the radius of gyration about center of mass of 0.125 meters. If the 20 kg gear rack B, this is 20 kilograms, is subject to a force of 200 newtons, it's constant. Determine the time required for the gear to obtain. So the time required for the gear to obtain angular speed of 20 radians per second starting from rest. The contact surface between the gear rack and the horizontal surface is smooth. So the hint is, well, the thing which I underlined, find the velocity or angular velocity, find the time required for the gear to obtain an angular speed of 20. Okay, V or omega is a function of time, principle of angular impulse and momentum. So let's start off with the free body diagram. So let's draw it for the individual particle. If you have to draw, we will draw a combined one later on. So this point O is pinned. So there's VO, HO, and then I'll call that capital Mg. We draw the free body diagram of B. So there's small mg, okay, there's, so there's n this way, so there's going to be n the other way, then small mg, then there is p. Is that it?
Okay.
There has to be friction, right? If there's no friction, if there's no F, capital F or friction force, then there's no way this disk O is going to spin, right? Because there's no force acting in the horizontal direction the way I've shown it, the only direction force. So there has to be a force of friction. In fact, it should be this way because it's opposing the motion of B, and it will be in exactly opposite direction on gear A. Okay, I should call this MAG because they have given names to A and B. Okay, so for this, well, one option is, well, let's think about what equations we can write. Since we've identified v as a function of t, so we know it's linear impulse and momentum. So the gear is the round gear, or it's called the, well, just called the gear. It's called the pinion actually, rack and pinion. The rack is the one which is sliding, is linear motion, and the pinion is the one which is rotary motion. So the pinion is about a rigid body. So it has, you can apply the principle of linear impulse and angular impulse, right? For the rack, which is the sliding body, it's a particle. There's no dimensions given to it. So it's a particle, so we can only apply principle of linear impulse. So one way to go about doing this is to apply one equation for the rack and two equations for the gears of the pinion. Is there a way we can make it simpler? If we take moments about point O, because we see that there are majority of the forces pass through O, right? So if we take moment about point O, then I think you wouldn't have to worry about, uh, you wouldn't have to write too many equations because all forces get eliminated, they pass through O. Okay, so that's one way to do it. Okay, so this is exactly following the procedure we used earlier, which is draw one free body diagram to it. But I'm going to try to do it in a different way. I'm going to try to do it with, I'm not going to draw a combined free body diagram and solve it that way so that you know how to do the problem in a different way. So let's just use these free body diagrams to write the principle of impulse and momentum. Okay, so let's write the principle of angular impulse and momentum for the gear or the pinion. Okay, so starting from rest, so the initial angular momentum is 0. We need to find the moment about point O for the gear. So the good news is that MA, VA, HO, and everything passes through O. So the only thing left is F, capital F. So capital F times the radius, let's call this the radius, dt. this is f times r is going to be positive, because if you take the moment about O, f is acting this way, it's going to turn the system in the counterclockwise direction, so it's positive, equals IO, which is m a ko square omega. Okay, but f is a constant. How do I know if it's a constant? Because p is a constant, so f would be a constant. So I can just write f r t2 minus t1 equals ma k0 square omega. So I need to find omega, but f is an unknown. So I cannot solve for omega because capital F is an unknown. So I better find an expression for f. So to find an expression for f, what I'll do is I'll try to write the principle of linear impulse and momentum for A. So let's use the principle of linear impulse and momentum for A. So ma v1 plus the net force dt t1 to t2 equals ma v, this shouldn't be A, this is for B, that's for the sliding part. Okay, so mb, the initial velocity of the rack is 0, starts from rest, so that is 0, so we need to write it, just 0, plus the net force is going to be, so that's the force in the horizontal direction, right? I could write the equation in the vertical direction, but doesn't make sense because velocities there's no motion in the vertical direction, so it's only in the horizontal direction. So F, the net force is going to be P to the right and F to the left. MB, and then there is V. So if the rack is not slipping from the pinion, then V equals omega r. No slipping. Okay, now P is a constant, right? It's given that P is 200 newtons. F is also a constant because, well, if P was a constant, then F has to be a constant. We know that from, if you write Newton's law along the x direction, then you see that the acceleration is constant. And that only happens when the forces are constant. So if P minus F is a constant, then it's simply T2 minus T1 equals mb omega r. So we have this equation. So 1 and 2 are two equations in two unknowns. The unknowns are capital F and omega, right? So if two equations, two unknowns, we should be able to solve it. If you solve for, my bad, by the way, this is known, this is an unknown. This is 0, this is 0. So this is an unknown, this is an unknown. So it's not F and omega, but it's F and T2. So if you solve for T2, you get 0.6125 seconds. That's the answer. You could also solve it with Newton's laws. Now, I'm supposed to do this chapter for this whole week. I'm going to take a shortcut. I'm going to move on to 19.3, which is supposed to be done Friday tomorrow. So I'll be done with not tomorrow, on Wednesday. So I'll be done with chapter 19 on Wednesday. So that will give us 3 days, this Friday and Monday and Wednesday next week. So 3 whole days to do review for the entire syllabus for the final exams. Okay. Yeah.
Do you know how the files we set up? Like previous session, we got our set up. How was this one set up?
No, so we've not yet met and decided, but I will let you know. Hopefully, we'll get. I'm not sure if I'll be able to do it before we We might, it might be during the study days, but I'll email you the details for sure. Yeah.
Is there any way that y'all could figure out like the week before instead of actually?
Absolutely. So I think I'm going to push to get this exam done as soon as possible. So we get the review out next week, around study days. Test is on 13th. You know what that is? That is, I think, 1 week from the last day. 13th is a Tuesday. Wednesday. The Wednesday, yeah. So 13th. So we try to get it